Thanks for coming. My name is Joxean, and I want to talk about a program diffing tool like bindiff, which is the more known tool, similar to this one, that I created myself. So, the name of that open source project is Diaphora, or Diaphora. The word comes from Greek. In Greek it means difference. It is open source, it's GPL, it's a NIDA plugin, at least for now. Maybe tomorrow it will become an independent tool, but for now it is specifically written for NIDA. And it's a tool for performing program diffing, which is typically referred as binary diffing. It can be used, for example, for patch diffing, finding how the vulnerability was fixed in a closed source product. It can also be used, for example, for porting symbols between IDA databases, or for finding new functionality that was added in a closed source product. It can also be used, for example, and is one popular use of such tools, for detecting plagiarism. If some company uses the source code of some open source project which forbids closing it, or some company just stolen the source code from another company and integrated it, we can, using binary diffing, program diffing, check if it is actually the same or if they share a big amount of the same code. First of all, I think that I have to explain why I wrote one more program diffing tool. There were many reasons to decide to write my own one. Just one more program diffing tool, because this is not the first one. There are so many. The main tool I used to use was Dynamics bindiff. It was unfortunately not updated lately, since, I don't know, maybe 4 or 5 years. And it lacks many features that I required and that I didn't understand why they didn't ask them. Maybe it's because they don't worry about such features, but I really needed them for me. Also, I was, before starting writing from scratch my own tool, I was taking a look to the open source approach that are out there, but either they were not as good as I expect, or I considered too hard to adapt such projects to my needs. So finally, and because I mostly prefer to write my own tools, I discarded all of them and started writing them, my own one, from scratch. More about the why. I typically work doing reverse engineering, and many times I need to port my work from an old version of my target to a new version. For example, if you are researching, I don't know, some specific component of Internet Explorer, and you have all your comments, the structures you created, I don't know, anything, and then a new version of Internet Explorer appears. You want all your comments, you want all your structures, you want all your enumerations, and etc. Should be easily portable between the old version and the new version. There are some things that can be imported, for example, with Dynamics bindiff, that commercial tool, but I'm a heavy user of structures, enumerations, unions, and also I do use a lot the decompiler, because once you apply structures, enumerations, unions, etc., you can have a very nice idea about the real aim of that function that you are researching once you are using them. It is easier than looking to the disassembly. But Dynamics bindiff, the best tool in the past for program diffing, this is my opinion, didn't support neither structures nor enumerations, anything else. So, when porting symbols from one database to another, I found also many cases where functions very similar in the pseudo-code, in the decompiled code, and very different in the assembly were missed by Dynamics bindiff. If you press F5 or whatever, and you see that different functions at assembly level actually translates the same C code, you know that it's the same function. But bindiff or other tools didn't apply any heuristic using the pseudo-code. I wanted to use it because I knew it would be better for having better matches. Also, in this sense, dynamic bindiff used to work really bad when you were matching, for example, one program for ARN and one program for AND64. Not comparing the same architectures, but different architectures. Well, in the past, before writing that project, Diaphora, I used to write many project-specific hacks, ugly Python scripts to port my structures to apply them, the unions, etc., etc., for each project, until I got tired and I decided that it was better to write a generic tool better than ugly hack scripts for every new project. The first version I wrote of Diaphora, this program diffing tool, it took me like a weekend, more or less, and at least in my test, it used to work better than dynamic bindiff, turbodiff, Darwin Green, and other tools. Okay, let's talk about how it works. Internally, Diaphora does the following. Simply, well, it exports its database that we are going to compare to my own SQLite format. Then I compare simply running SQL queries, all the artifacts, all the attributes from both databases, and I show the matches in either, as simply as it sounds. However, naturally, it is more complex than that. Okay, how it works. When exporting, it exports the following. From each database, the following elements, like functions, all the related attributes to the functions, like flags, the prototype, the relative addresses, the number of basic blocks, the number of heads, the cyclomatic complexity. Also, all the related information for the basic blocks, all the related information for the instructions, the pseudo-code, the decompiled code of each function, also the abstract syntax tree, the AST, of each function, the pseudocode. The abstract syntax tree is a structure that explains how the pseudocode, how the code from a language is expressed. Okay, for each function or basic block, also some information is calculated. I prefer to calculate such things at export time because you export once and then you diff a lot of times. Some of the things that I calculate are, for example, a hash basis on the bytes. This is the non-changing bytes of each instruction. If it is, for example, move EAX, some offset, I discard the offset and I only take the bytes that will not change because of relocations or because of the displacement. I also calculate the cyclomatic complexity of each function, the strongly connected components of the flow graph of each function, the topological sort of the flow graph, the small primes product, I will explain it a bit later, for each strongly connected component, a set of 3 fuzzy hashes of the raw pseudocode text, and also a fuzzy hash based on the AST, the abstract syntax tree of the pseudocodes. Well, it is, again, another small primes product that I will explain later on. Also, I calculate the number of loops, and I extract all the switch structures, like all the values that are used in the switch, all the switch cases. Okay. Also, at the database level, not at function level, I also export the following. A fuzzy call graph has biases on the small primes product of each function's cyclomatic complexity. That's it. For the cyclomatic complexity of each function, I assign to the corresponding cyclomatic complexity a prime number. Then I multiply all the prime numbers of all functions, and I use it as a hash. This is the fuzzy call graph hash that I calculate. I also store all the primes that I used for the calculation, so I don't have to reuse them again. And also, the small prime product hash of the call graph will be used to determine how related two binaries are. It can tell you if the call graph of the program is equal. So if it is equal, it is supposed to be structurally the same program, or if there are very little changes, like the color of changes 0.1%, you know that it is like 1 or 2 functions that were changed. Okay, comparison. When comparing two IDA databases, and as for now, Diaphora only can compare two databases, it cannot compare, for example, a directory or something like that. The two databases that are exported to the SQLite format, understood by Diaphora, are simply compared using SQL queries with all the attributes that were extracted before. The SQL queries launched try to match as much arguments as possible using many different heuristics. First, the most robust ones, the heuristics that are likely going to cause the fewer number of false positives or lambs, and then the less robust ones, the ones that are going to cause a lot of false positives. Then, for this match, a similarity ratio is calculated and assigned. And finally, the results are simply labeled and grouped as either best, partial, or unreliable. Okay, as of today, Diaphora has 44 heuristics implemented for finding matches between two different data databases. Some examples are, for example, equal or similar, both assembly or pseudocode. It means if the assembly in the two databases is the same, we have a match. If the assembly is different, but the pseudocode is the same, we have a match. And also, I do it with row. With row, I mean the assembly as you get it from IDA, or the pseudocode as you get it from IDA, and cleaning it up. For example, if you have expressions like, I don't know, offset, OFF, underscore, some address, I simply remove all of these parts and then compare with the cleaned up version. Some other heuristics are the byte hash and name. If the hash I calculated with the non-changing bytes of each function and also the true names referenced from both functions are the same, we have a good match. The same function name, if we are reversing engineering, for example, patches from Microsoft, we have some partial symbols, so we can simply compare the function names, and that's all, we have a match. Others, all or most attributes from the function, like if the number of basic blocks and the number of heads and the cyclomatic complexity and the number of imported function is actually the same, we can conclude that it is actually the same function, so we have a good match. Others can be another variation of this, the same address, nodes, heads, and primes. Primes is a prime is assigned to each mnemonic, to each instruction, to each assembly instruction, and then all the primes are multiplied together. And if the final hash is the same, the primes, we consider that it is the same function, but that maybe some instructions were reordered. And a lot of other heuristics. I will explain in more detail some of them later on. Okay. So, for each match that we have from the SQL queries that we run, a similarity ratio is calculated using 3 methods. The first one is the easiest one. I simply use the sequence matcher quick ratio function or member function from Python, comparing either the assembly or the pseudocode. It basically gives out a similarity ratio between two strings. So using a cleaned up version of the assembly and the pseudocode, we have a pretty good way of comparing how related one function is to another when we have a match. I do it with both the raw version of the assembly and the pseudocode, and also with the cleaned up version of the assembly and the pseudocode. Also, I calculate the difference ratio based on the small primes product of the abstract syntax tree. It is, for each expression or for each instruction element in the abstract syntax tree, I assign to it a prime number, then I multiply all of them, and if the hash is the same, even if structurally the AST is different, the tree looks different, we can conclude that it seems to be the same function, but maybe with reordered instructions. And that's it. What I do in this case, in the case of the AST small primes product based hash, is I remove all the primes in both sets, and I only consider the primes that are in one of the two sets that were not in both sets. I calculate the similarity ratio based on that, and that's all. Okay, then according to the ratio, the matches are grouped in a set of either best, partial, or unreliable results. The best results are those with a similarity ratio of 1.0. So, for example, if you are looking for how one vulnerability was fixed or patched, you simply need to ignore everything in the best matches window. Partial results are those with a similarity ratio bigger or equal to 0.5. In general, some heuristics are considered reliable even when the ratio is lower than 0.5. For example, the same name heuristics compares functions that have the very same name. No IDAs generated names like sub underscore some address. Only true names. Like, I don't know, create file or something like that. For example, when comparing Microsoft patches, it helps a lot. And even if one function was heavily modified, when the similarity ratio is like 0.2 or something like that, we know that still it is a good match because we have partial symbols. Also, the last results are the unreliable ones, and these are those with less than 0.5 similarity ratio, or the heuristic that found the match or matches is known to cause too many false positives. For example, I use one heuristic that simply compares the number of loops in a function. If a function has, say, 5 loops, it is a very small number of loops, and it can cause a lot of false positives. On the other hand, if we have like 100 loops in a function, the same, we know that it is going to be a good match, but it's not going to happen very often. So this one is considered as overall an unreliable or experimental heuristic, and by default, all results, matches, or found by this heuristic are automatically labeled as unreliable. Okay, some heuristics. There are, as previously said, many heuristics that I use in Diaphora. As of today, 44. Some of them are rather simple, for example, the same name heuristic, and others are really complex. Some of them are very reliable, like the same number, the same name, and others are rather unreliable, like the loop number. Let's see some of them. This is one that we already discussed about a bit. Sorry. The heuristic byte, hash, and names. So it simply compares the non-changing bytes of each instruction and the references through names. If the bytes from the instructions, from the assembly instructions, are actually the same, and the true names of, I don't know, constant uses or global variable names are the same, we know that we have a really, really good match. A true name is a name like a function name or a string reference with a name that is not auto-generated by IDA. So it is not a sub underscore an address or of underscore an address or dbl underscore an address. This is one of the simplest and best heuristics that is already implemented in Diaphora. Some more. Oh, sorry. This is the whole code of that heuristic. Remember that I calculate everything that I need at export time. So export time is when most of the work is done. And at comparison time, I simply run SQL queries. This is all the heuristic in this case. It simply compares from both databases if the names are the same, and the byte hash is actually the same in both databases. Okay, this is one of the most common heuristics in program diffing tools. Such an heuristic is available in Dynamics bindiff, Darren Green, TurboDiff, and in any other program diffing tool. In Diaphora, I have many heuristics that are actually specific to this tool. Some of them are the same cleanup assembly or pseudo-code, because it's the only tool that is using the pseudocode as of today for finding matches. The pseudocode fuzzy abstract syntax tree has, as previously said, as it is the only tool using the pseudocode that the compiler it is specific to Diaphora, the strongly connected components small primes product, although it is based on the graph, and most of the program diffing tools have heuristic bases on the graph. As far as I know, is the only tool using that. And for example, switch structures. Okay. How it works is heuristic, the same cleans up assembly or pseudocode. It is partially based on the pseudocode generated by the XRISE, the compiler, naturally. It generates a clean textual representation of the assembly, pseudocode or both, that can be used for comparing. For example, if you have an instruction like move EAX sub sonality, it will simply remove the part that is auto-generated by IDA, and it will be like move EAX XXX. If we have in the pseudocodes, in the compiler, int b1 equal to b2 plus whatever, it will remove the auto-generated names for the variables. And it will be like int x equal to x plus the constant. This is a very simple heuristic that works pretty well overall and causes a very low ratio of false positives. This is how internally the heuristic works. This is the cleaned up version of the assembly for both databases. As you can see, there is no label, there is no IDA auto-generated name. So in this example, this is the Avast program, the Avast antivirus for Linux. We have the Argus match because we know that engine error is the same function in both databases. And the only thing that is changing is actually this one. There is an IDA's auto-generated name, and in the other database, we have a proper name, engine errors. I only remove IDA's generated names. Yep. And I don't remove the names that are actually good names. Some people told me that this maybe is an error because it should also ignore all names. For example, in this comparison, the similarity ratio that is generated is like 0.99 or something like that instead of 1.0. If I remove that name also, the engine errors, the similarity ratio that it will generate will be 1.0. However, I prefer not to do so because in this case it is clear that it's the same function, but in other cases, let's say that it is a function call that I removed or I ignored the name, and we are matching, for example, a function that is adding an element to a list with a function that is removing elements from a list. This is one reason why I don't do that. Writing heuristics also for program diffing tools is harder than what it looks before you actually start writing such heuristics. Because when you start doing it and trying to compare to match anything, and no heuristic written with not very carefully is going to cause a gazillion false positives, and you don't want to have false positives. Okay, one more heuristic. Pseudocode fuzzy abstract syntax tree based has. It is based naturally on the XRISE compiler. For now, tomorrow I plan to use also the Snowman compiler, which is open source. It takes its expression, C instruction T in the ASC, and assigns a prime number to it. For example, the if instruction is 2, the do instruction is 5, the switch instruction is, I don't know, 13. Then all the primes that are assigned are multiplied together, and a fuzzy abstract syntax tree has is generated. For now, only perfect matches, those for which the final has are equal, are considered. In the future, I will also consider partial matches, where not all the primes are the same, but say, I don't know, the 90% of them are actually the same. For non-trivial functions, I mean for big functions, functions with a good number of instructions, it really generates or finds good matches. More, the strongly connected components small primes product. Using the small primes product again, as with the previous heuristic, it assigns a prime for each strongly connected component based on the number of strongly connected components of each function. The final product of the calculated primes is a hash, and as before, only perfect matches are considered. In the future, partial hashes will be also considered, but not for now. Okay, switch structures. It considers the total number of cases as well as the actual values of the switch structures that are used to match functions. There are some switch values that can cause a lot of collisions, like if we have switch, whatever, case 1, case 2, case 3 default, which are pretty common, but other cases are not that common, like switch, whatever, case 0f1f02, or cases that are uncommon. In such cases, this heuristic also actually finds very, very good matches that other tools miss overall. So before implementing it, I thought that that heuristic will cause too much false positives and will be very unreliable. But the reality proves otherwise, because it works better than other heuristics that I saw at first that will cause little or no false positives at all. It is very different what you have on mind before writing such a tool to what you really find when you start writing such a tool. Okay, time for a demo. I will start with some very small samples, then an example where I will simply port symbols from one database to the other, and also how to find new functionality. Okay. Give me 1 second. Can you read it? Yep. So this is an horrible written program with 2 vulnerabilities at least, okay? So it takes whatever is given to the program, copies it into a stack-based buffer, and then printfs it out, okay? Oops. This is a second version with at least one of the bugs fixed. In this case, instead of copying anything that is passed to that function, it is only copying the exact amount of bytes that the stack-based variable is long. And then, anyway, it prints out again. And the final version, where it doesn't have anymore the format string vulnerability. Okay, so I compiled both programs, the C programs, with a compiler for X Intel 886, for AMD 64, and I didn't have for ARM in this computer, but anyway, I could have done the same with a MIPS compiler or whatever. Also, I have done it for Windows and for Linux. I will start with the very first program, this one. Okay, this is the very first program. Here we have the main function that calls the foo function that calls the string copy, printf. What I will do now is I will simply export this program, this data database, to my own format. This is the script that I have to run, Diaphora. It is completely written in Python, so you can simply run it from here, like this. Okay, this is the small window of Diaphora. It asks for the path to store the database that we are going to generate to export this data database. We can simply press OK to the default options. It asks if we want to rewrite it, because I already have it generated. It starts exporting everything if the bin code won't. Okay, Everything is stored. This database is rather small. And now I'm going to open the seconds binary. No, not this one. Okay. This is the second version of the program where the string copy back was fixed. Again, I will run the Diaphora script, but this time I'm going to use one more thing. First, yes, I want to export the current database, but I also want to diff against the previous database, which was test1 SQLite. Press OK, say yes, because I want to overwrite the previous one, and it starts compiling. It first exports, and it says, the call graph signature, do you remember the small branch product I said that I calculate from the call graph? The call graph signature for both databases is equal. The program seems to be actually structurally equal, which actually are. At function level, it's the same program. But at instruction level, it isn't. If we go to the best matches window, I will close it. We will have all the best matches with a similarity ratio of 1.0. And the description, the heuristic that actually forms such matches. Okay? If we press right click, we can diff the assembly. In this case, it's actually the same function, so we have no change. We can diff, for example, the pseudocode. We are going to do it later on. We can diff in a graph instead of watching only the pure assembly instructions. We can watch the graph, the basic blocks. Let's go to the partial matches window this time. Here we have some best matches, which are in red, with a similarity ratio of 0.0, because yeah, both names look very similar, but are actually not the same function. We can ignore them. And then we have a very, very good match with a similarity ratio of 0.89. It says that the pseudocode is very, very, very similar. If we right-click on it, diff pseudocode, yep, we will see that the only difference is that it is calling now Esther and copy instead of string copy. So how the developers fixed that vulnerability? It is very clear in this diff. Let's do the same again, but with the other database. This time, I will open the series one. I will close this. And I will run the third one against the second one. Okay, yes, we want to overwrite. And it starts finding the matches. Well, first it starts exporting the database, and again it says the same. The call graph for both programs is actually the same. And then we have to go to the partial matches, where we only have one single partial match because all the other matches are best matches. And we can right-click, diff pseudocode, and check what was fixed. The compiler uses in the last version puts, because in the last version puts, and before, no, sorry, the other way around. Uses puts and translates to printf. In this case, we have the destination, which was the local stack variable, but in this case, the compiler is storing back. Well, anyway, the vulnerability that was fixed is actually clear in this code because it is in the printf code. These examples are very, very, very easy, but can show how the tool works. We can match programs for different operating systems or different architectures. For example, I will use test one. Where is it? This is the same program, but for Windows. We have here the functions with the symbols. I will export it and compare to the ELF version. This is the program. This is the test 2. It will compare the second version of the program from Linux to the first version of the program for Windows. It is now exporting. And here we have the partial matches. We have to consider that the program are for different operating systems, or even in the case that we have the same name, it cannot be considered best matches, but partial matches. Here we have the full function, the one that we patched. If we right-click, we have the pseudo-code, and we can check what was changed. In the first database, we have the string copied, and in the second one, the str_n copied. One more demo. This is the Avast binary for Linux, for AND64. We have a lot of symbols because they didn't strip them. We have, if I remember correctly, also some structures. Yeah, we have a lot of structures, okay? We can export everything, the structures, the enumeration, the names, the comments, and everything from this database. I already have everything stored in this database because it takes some minutes. And now I will going to open the database for the binary, but without symbols. This is the stripped version of the very same program. We have some functions, but not all, as we can see here. We can do is simply compare this version to the previous one, which is this one. I will say small functions. Press OK, say no because we don't want to overwrite this time. And it starts running all the heuristics to compare the functions from both binaries, and after a while, it will show all the results. Let's give some time. It takes a while. This is one of the slowest heuristics. It's going to find it very soon. And come on, baby. And here is it. Okay. From 1,678 functions in the program, we already matched with a similarity ratio of 1.01646 functions. If we go to the partial matches, we have only 4 functions that were actually partially matched. Remember that this is actually the same binary. And now we can simply import everything from the database with symbols to the database with no symbols. If we check the structures, enumerations, etc., etc., we will see that we have some of them, 73, but not all of them. And now I will simply import everything. Right-click, import all functions. It asks, do you want to import everything? Yes, we want. It imports all the structures, enumerations, etc., and updates the current database. Changes the names, update the comments, update structures, enumerations. And well, it's going to take a while because it has to update everything. finish it. Okay, this is how it works. I already shown it with some demos, and I already explained how it works as of today, but I have many changes on mind. As of today, it works in some sense better than dynamic bindiff, but not always. For example, dynamic bindiff works very well with comparing different architectures, binaries, which are not Intel 86, AMD 64, and ARM. For example, if you want to compare one Spark binary with a PR-RISC binary, which is very crazy comparison, dynamic bindiff works better for now. I have some improvements on my mind to be better, works better than bindiff. Some of the improvements that I have in mind are more heuristics, like using an intermediate language instead of using raw assembly, apply optimizations over the intermediate language, and then compare the intermediate representation. It all gives good results, and it could be used to compare anything, like, I don't know, MIPS to Spark. Also, I plan to use, based on this intermediate language, symbolic execution. The symbolic execution of basic blocks from different architectures are actually going to give the same results. So, no matter if the instruction set is in one MIPS and in the other PPC, if the final result of a basic block is actually the same, it is actually the same thing that is being done in the basic block. As of today, I'm using BEX. BEX comes from Valgrind, so any instruction set supported by Valgrind will be supported also by Diaphora. Also, I plan to create an independent GUI tool so it doesn't depend on either. And this is because some people asked me support for Radare, or asked me support for Snowman, or asked me for support for Hopper. Well, only 2 guys, but there are some people that asked me for support for it. And in the not so near future, I want to improve it in the sense of adding a way to match directly a binary from source code. What about finding matches between the C++ source code that you have from some application, let's say OpenSSL, to the binary that you're analyzing, that you know that statically links the OpenSSL code? So you don't have to lose your time analyzing the OpenSSL related functions in your commercial product. You simply compare them and import all the symbols, and that's all. I plan to use it comparing the abstract syntax tree from both the source code and the decompiler generated one. It's not easy at all. I plan to do it in maybe, if I'm lucky, and I have enough time, in 2 to 3 years, so it's not tomorrow. Naturally, I need a fuzzy C++ parser to generate the abstract syntax tree from C++ source or C source, but this is a non-trivial task that by itself is a whole project. So it's not going to be available tomorrow. And for now, this is all. Diaphora is open source, GPL, so you can use it, modify it, adapt it to your needs, and if you want, you can send me back patches. This is the URL of the project, and that's all.